Thank you very much for the introduction. So I'm Damian Ndiwago. I'm a PhD student supervised by Christophe and Jack. And I'm also supervised by researchers from the Luxembourg Institute of Science and Technology. So that explains why we are also working in hydrology. So this study is about Bayesian model selection applied to hydrology. And the presentation is I'm going to begin with an introduction, then I'll talk about our model formulation, then how we have implemented these techniques both on synthetic and on real-world data. So for the introduction, hydrology is the study of movement of water in the environment. And the main processes that hydrology study on the macro scale are precipitation, so how water leaves the atmosphere and ends up in our rivers and other water bodies. And we also have evapotranspiration, which is also a key process in hydrological models. So how this water eventually returns back into the atmosphere. And in order to better understand these processes, hydrologists have formulated several models. And these models differ in terms of the concepts behind the models, the parameterization, and also the structure of these models. And some of these models have been very successful in predicting events such as flash floods, and they are also used in insurance company for asset pricing. So one of such models that has been highly successful is, oops. Sorry, yeah, so it's the, I just call it by the acronym HBV model. So what the HBV model does is that it describes the dynamics of water in various catchments. And the model has been very successful such that by 2006, it was being used as a standard in more than 50 different countries. So our model formulation is based on the HBV model. Like all the other speakers have already said, for these models to be useful, we have to estimate the parameters. And the Bayesian approach is widely used in hydrology for the parameter estimation. However, what is lagging behind is model comparison. And in both practice and in academia, hydrologists are of the consensus that Bayesian model selection is necessary. But however, there is very little practice in terms of that, of applying the Bayesian model selection. And some of the reasons in literature is partly because the full Bayesian approach for model selection involves thousands of likelihood evaluation for moderate number of parameters. And so the computational expense is huge. And then we also have so even though algorithms like the random walk metropolis are very successful, but for models where the parameters are highly correlated, they perform very poorly, so they are not that robust. And in order to implement algorithms that are highly robust, like gradient-based algorithms, these require rigorous technical and mathematical expertise. So it's not really available in the hydrologist toolbox. So that is where our contributions come in. So we have an algorithmic contribution, and then a statistical contribution, and a methodological one. So for the algorithmic contribution, we've merged two major existing algorithms, Hamiltonian Monte Carlo and replica exchange. So while replica exchange is not new, and others have done that, they have combined this with random walk and other algorithms that make it not very efficient like what we have done. So by combining it with HMC, it is very robust and it scales well in high dimension. Then we've also gone a step further because even across various fields like in biostatistics, because I did some analysis there, they do model selection, but sometimes they don't go further to see if these models can actually fit the available data. So we've gone further to implement formal testing for which we call posterior predictive checks for these models, such that it can also tell us if there is prior data conflict. And for the methodological contribution, we have what we call, what we've implemented, a framework in TensorFlow probability, which is very fast. So I'll now talk about the nature of the data. So the data we use is time series data from Magella Creek in Australia, partly because we wanted a data set that does not involve other variables like snowfall, just rain and maybe sunshine. So Magella Creek in Australia has data for from 1980 to 2006, but since the first study we are doing is for illustration, we use just 1980 and the first 3 months, partly because those are the months where we have rainfall events almost every day. So we can see that on this axis is the discharge, which is our variable of interest, and then there is precipitation. So what is exciting about this graph is that we can tell that when there is a high amount of rainfall like here, the discharge from the creek is huge, and then this can lead to flooding events. And then other variables of interest, like I already said, are the precipitation and the evapotranspiration. So I'll now talk about our model development. So like I said, we developed our model to mimic the HBV model because it's highly successful. So our model development is based on the conservation of mass. So if we consider the layers of the Earth as various buckets, in hydrology, such models are also known as bucket models. So precipitation that leaves the atmosphere, part of it ends up in the first layer or bucket, V1. Then part of it goes down, while part leaves as discharge, Q1, and part returns back by evapotranspiration. So therefore, we can write a first ODE as this equation where precipitation minus evapotranspiration and the other quantities of interest. So the idea now is that if we have multiple buckets, a second bucket, right up to n buckets, we have different numbers of parameters as the number of buckets increases. Then we have different numbers of systems of ODEs, and we will use a full Bayesian approach to tell which model can actually fit the data best and also is parsimonious. So since it's a Bayesian approach, we have to define our likelihood, and in that light, we first of all introduce some notations. So here, Y represents the discharge, while GOPS and GSOL are known as observation operators. So GSOL actually solves the ODEs for us, while GOPS enables us to observe the results at specific time points. And of course, ITA is the noise which we assume to follow a multivariate Gaussian distribution. And so this one is a schematic view of what is happening. So theta is the parameter vector, and then GSOL is the solution operator that runs the system of ODEs, and then GOPS gives us the results. And so this is the full likelihood that follows a multivariate Gaussian distribution. So since we are using the Bayesian approach, we restate the Bayes theorem such that we include an explicit indicator term for the model. So if we are using 2 buckets, it becomes M2, 3 buckets, and so on. And in the full Bayesian approach, the quantity of interest is the marginal likelihood. So this brings us to what is known as the Bayes factor. So in this approach, for 2 models being compared, let's say model I versus model J, the ratio of the marginal likelihoods, which is the Bayes factor, is what is the criteria we use to compare these models. And since it's a ratio, if it's greater than 1, model I will be preferred. But there's also a table for the interpretation of the Bayes factor that tells us what weight of evidence to attach to the model. As we can see, the marginal likelihood is an integration problem, which is has no closed form solution if the prior is not conjugate. So therefore, this brings us to computational aspects. It becomes a computational problem as well as a numerical problem. And in that light, that's where our algorithms come into play. So we use what is known as thermodynamic integration. So there are other methods for this in literature, but they do not really work for this type of models. So we use thermodynamic integration because it's well suited for high dimensional integrals. This is also found in the literature for numerical analysis, and it does not involve choosing ad hoc distributions, which is usually referred to as proposal distributions. And the restriction with these distributions is that they have to overlap with the posterior, which is difficult in practice to tell beforehand. And then we use gradient-based samplers, partly because they scale well in high dimensions, and the one we use is Hamiltonian Monte Carlo. And by combining it with replica exchange, this leads us now to the new algorithm which we introduced called replica exchange Hamiltonian Monte Carlo. But then I will talk first about thermodynamic integration. So it's a technique from statistical physics, but then re-derived in Bayesian statistics, such that in order to derive it, we state the full likelihood, the marginal likelihood in this form, but then we raise the likelihood to values which we call inverse temperatures, beta, between 0 and 1 inclusive. So the idea is that when it is 0, then we are just sampling from the prior distribution, and 1 from the full posterior. And since it's convenient computationally working with logs, we take the log of this site, and then by applying the chain rule of differentiation, we end up with this, and then substituting this here. Therefore, end up with this after applying this identity for differentiation of exponents. And then we arrange this such that we can recognize this as the posterior distribution, where the likelihood is raised to beta, such that it becomes the expectation with respect to the values of beta. And then the log marginal likelihood, therefore, is this integral 0 to 1, which therefore becomes a numerical problem solved using any discretization method. In case we use trapezoidal rule and then replica exchange Hamiltonian to get the samples from here. So now I illustrate I talk about the replica exchange algorithm. So what happens is that we run several chains which we call replicas in parallel, where the likelihood is raised to values between 0 and 1. Then we have local updates where the proposed values, just like in Metropolis, random walk Metropolis, are either accepted or rejected. And then we have global updates where adjacent chains try to swap their values, and they're either accepted or rejected based on Metropolis-Hastings algorithm. And by so doing, it converges very fast compared to any other algorithm out there. And then we use all the samples to get the thermodynamic estimate of the marginal likelihood. And then the good thing about this approach is that we can also get the posterior parameter estimates, the summary statistics. So when the likelihood is raised to the value of 1, then we just get the posterior estimate since it's the full posterior. And in order to illustrate the effectiveness of the algorithm, we have here all these distributions, Gaussian rings. So it's a mixture of Gaussian distributions, but then we center them at 0. Then we make sure that they are totally isolated. So this is where the replica exchange shines, because if we use any other algorithm out there, if the initial values are from this side, then it gets stuck. From this side, it gets stuck. It cannot sample across this barrier. For instance, NOTS, which is an advanced implementation of HMC, was unable to give us the target distribution, which is this. But then when we use replica exchange, Hamiltonian Monte Carlo, we can recover the full distribution. And we tried this right up to 100 parameters, and it's also very fast. It takes just a few seconds. And random walk Metropolis is unable to do this, especially when the parameters were highly correlated. So therefore, now I'll talk about the data, the results which we obtained. So we generated data from a 2-bucket model and also from a 3-bucket model. And then, of course, since it's a Bayesian approach, we had to give prior distributions, which we use log normal priors because it's a go-to prior that most people use. And then secondly, the parameters have to be positive. And most importantly, too, what we notice is that using log normal priors, the model converges very fast. And of course, for the variance, we use inverse gamma distribution, even though we also tried other distributions for it. But inverse gamma was really good. And so we computed the marginal likelihood for all these models 15 different times on the HPC of the University of Luxembourg. And in each of these cases, we could, the marginal likelihood calculated was highest for the discharge generating model. Like in the first case where the model was generated from the two-bucket, the data was generated from the two-bucket model. You see that it has the highest log marginal likelihood. For the second experiment from the three-bucket model, which has more parameters than the two-bucket, but less than the four-bucket, the model M3 was selected. And based on the table for the weight of evidence, we were at the highest level of evidence for this, which is decisive. Then we also applied this to real-world data, which I will talk about it. But then this is a plot of graphical posterior predictive check. We developed a test for posterior predictive check, but I don't show it here because it's a little bit long, for formal posterior predictive check, where we also had something like the p-value in the similar to the frequentist. And the good thing about our test is that it can also tell us if our prior is in conflict with posterior. But in this case, we use the posterior samples here to generate the discharge data for each of the models. So, and then we make a plot now of the discharge. What we can see here is that all the models fit the data very well. So therefore, it would be difficult just by observing to tell which model is actually the data generating model. So that's where the bias factor now could tell us, okay, they all fit the data very well, but the model with the least number of parameters was penalized less. And the good thing about the marginal likelihood is that there are several proofs for it. It implicitly penalizes for the number of parameters, taking into account the information gain. So if we compare to the AIC and the other approaches where we have to implement an explicit penalty for the number of parameters. So for this, we don't need an explicit penalty. And for the real discharge data, so we fitted the three models, and these are the parameter estimates. And what we can see is that the three-bucket model was preferred, so it has the largest likelihood. Also, for the parameter estimates, can see that for some, the credible interval is narrow, but for some it's huge, which that's because we are still kind of developing the model. We tried on 1 year, a period of 1 year, such that we can use the entire data set. I hope that will reduce the variance in the model. So to conclude, we have introduced a framework for full Bayesian model selection that enriches the hydrologist toolbox that can simultaneously do parameter estimation, model selection, and also posterior predictive checks. And we also introduced a gradient-based algorithm called replica exchange Hamiltonian Monte Carlo that can be used in any discipline, in any field, and it is very fast. And we've implemented it in the free software TensorFlow probability. And the good thing about this is that it's faster than any other statistical package out there, STAN, PyMC, and most statistical models have already been implemented in TensorFlow probability. So it makes it available for anyone to use. And finally, thank you.